Okay, so now let us take the next step towards completing the Maxwell's equations. This is something that are familiar, but you have to adjust this knowledge of this phenomena into the framework of electromagnetic theory, which is Faraday's law. Lecture 8B1. So Faraday's three experiments of 1831, okay, went down as classic experiments uh, to establish this part of the physics. First, of course, there is a magnetic field, constant magnetic field, let's say going in, and it is circuit, and then you move the circuit with velocity v, and then you will get a current that you have already done. This is nothing. Faraday also um, saw that there's a current flows, and which we have now discussed as motional EMF. There's a moving circuit, and that creates an EMF in the circuit, and that sends a current. That was experiment number 1. Okay, pulling the circuit to the right through a magnetic field makes a current flow in the loop. That's experiment 1. Then, of course, the next obvious experiment is keep the circuit constant and make the magnet move. Okay, so that's relative motion. You would expect something to happen, but I am still in the laboratory frame. So experiment number 2 is pulling the magnet to the left, holding the loop still. Again, the current flows in similar current. If the velocity is the same, then the similar current flows in the circuit. Most crucial again is experiment number 3, in which the magnet is constant, the loop is still, but you are changing the magnetic field as a function of time. So that's experiment number 3. Okay, with both the loop and the magnet at rest, change the strength of the field. Once again, current flows in the loop. These 3 experiments had to be explained. Of course, Faraday knew that moving charge experiences a magnetic force. But in experiment 2, there is no moving charge. Charge is yet still. So why should there be a current? In experiment number 3, the charge is yet still, and the magnet is yet still. So in experiment number 2, we can, of course, Faraday knew nothing about relativity. Okay, so if the observer were sitting with the magnetic field, then of course there will be relative motion. Then one could relate it to the first experiment number 1. But I am sitting in the lab scale. There is no movement of the charge, and hence experiment 2 and experiment 3 seems different than experiment number 1. Right? So of course that we don't have to go to great length to understand this now because of the Faraday's ingenious conclusion, okay, that the changing magnetic field must be causing an electric field. That was the uh, crucial insight that came from these 3 experiments. So if EMF produced when the circuit is at rest is same as that given by let, let's say E dot dl, that's the EMF definition, is minus d phi by dt, okay, as the same if you have even if you have the current magnetic field changing, okay, so there must be some electric field uh, associated with change in the magnetic field, which can move the charge. And what can move the charge? Only an electric field can move the charge. And hence his conclusion that there must be an electric field associated with the change in magnetic field, with changing magnetic field. So that we can write down that E dot dl, that is EMF, again, okay, with minus changing field through the surface dot dA. So that is, it also looks like a change of flux, but for a different reason, not because of movement of the circuit, but because of the changing field itself. Okay, so it's an integral and it's a partial derivative. That is, I'm looking at the explicit dependence of B as a function of T. Okay, so that must be experiment 2 and 3. So we can invoke now Stokes' theorem. So this is a line integral. I can convert it into a surface integral. On the right, I have a surface integral. So I can convert it into a surface integral, and that would be curl of E dot dA is minus dou by dou dt dA. Remember, curl of E in electrostatics was 0. But here, one is attributing to curl of E a, a, as a source of del by del t. So if this is for arbitrary surface, okay, and hence it in differential form, this must be equal to, so del cross E, curl of E is minus del b by t. So no longer, okay, is del cross E, curl of E is 0 if there is a changing magnetic field. That is the contribution, a new contribution to what we have done so far, okay, from Faraday's law. So this is the Faraday's law, really. All right. Um, so, and this is new physics, not just Lorentz force. Okay. So what we had done, motional EMF was Lorentz force, but attributing a new E, okay, to minus delta B by delta T. Now this minus, of course, okay, is says that it's related to Lenz's law, as we know. All right. So we'll see its manifestations. So now this form that EMF is rate of change of flux, of course, with the same minus sign. Okay, is I had called it flux rule. So it is the same method for two different mechanisms. Okay, note the total derivative. Now we are not finding only explicit dependence on uh, time, but we are saying it's total derivative of the flux. So the total derivative would include any change in flux. Okay, with moving circuit also there would be a change of flux in time. Okay, because there is moving, there's a velocity v, and there is also flux changing. So flux rule is really the same method for two different mechanisms, or as Griffith says, it's is two twins. Okay, that doesn't mean they're the same. Okay. If two persons of two different names, doesn't mean that the two persons are the same. So flux rule is something that is a procedure which will give you the same answer for the two cases, but there are intrinsically two different mechanisms, at least in the laboratory frame. Okay, so in fact, in all frames, that is exactly why Einstein started his relativity 1905 paper from which was based on this electrodynamics and reference frame. So let me come to the Faraday's law. This is note that is a partial derivative with respect to time because of the claim is that this electric field is associated with the explicit change of magnetic field. Okay, and of course, sign is consistent with Lenz's law. That is, nature abhors, okay, or tries to avoid or opposes any change in flux. Okay, so we attribute this minus sign to that. So this is a new kind of field. Okay, so this let me call it for the moment as a Faraday field. So its comparison with let's do is comparison with Ampere's law. Why comparison with Ampere's law? Earlier, magnetic field, the source of magnetic field came from electrostatics from Ampere's law. that is, there is a mu naught J. Okay, so del cross E was mu naught J. Here is saying that uh, uh, there is a del cross E, there is curl of E because of minus dou B by dou T. Okay, so there are two kinds of electric fields really looks like. Okay, that is, if I have curl equal to 0, and then if I have curl is of E is minus dB by dt. So that is, and along with that, what is the, if curl of E is 0, then what is the source of the field? Is rho by epsilon naught. But if there is no rho, there is no charge, only changing in magnetic field, okay, then also I can have electric field, and this, there can be no, there need not be um, any charge at all. Okay, so uh, so this is, of course, is electrostatics. Okay, electrostatic field and Coulomb's law, or Coulomb force. And this is induced electric field. This has been induced by the changing magnetic field, and hence we call it the induced field. And this is the Faraday's law, the true Faraday's law. So, but this is the same E, which makes charge move. Okay, so for solving problems, one can exploit analogy between this source terms of induced electric field and the magnetic fields. Okay, that is, we know Ampere's law, del cross P is mu naught J. Okay, and that is, uh, uh, and we know divergence of V is equal to 0. All right, so you can see that. On this side now we saw del cross E is minus del B by del T, and there is no source charge. So del dot E is equal to 0. So it's formally similar, okay, except that mu naught J acts as the source term here, okay, and minus del B by del T acts as the source term in Faraday's law. Okay, and hence all the tricks and of the trade that I could use to obtain solve these problems, I should be able to do that. All right. So Faraday induced electric field are determined by minus del by del T in exactly the same way as magnetostatic fields by mu naught J. That is a formal equivalence. Okay. Hence, we can use all the tricks associated with Ampere's law, especially in the integral form, to find the induced field by Faraday's law. For example, we know that E dot dl is minus d phi by dt, okay, is the integral form of del cross E minus del B by del T. Okay, so and hence we can, so we know many techniques of how to solve this. B dot dl is mu naught ing, that comes from Ampere's law. So all the techniques that we thought, choosing an Amperian loop, and then solving for and looking for symmetry, and then solving for B, will work here. That is, you can now take a sort of an Amperian loop, but not now for B, but for induced electric field, treating minus d phi by dt as the source term. Okay, we'll just show through an example, but that is the power of this formal equivalence. So the rate of change of magnetic flux plays the same role as mu naught I ENC in Ampere's law. All right, the enclosed current in Ampere's law. So let's take a quick example, swinging magnet through coil. This is an experiment that you are going to do in the lab when you come back to the campus and do Physics 101, which is the experimental lab. Maybe you will be doing it sitting next semester, sitting at home and connecting through online through our equipment here in the lab. Okay, so and you have done this problem in JE, I'm sure. Okay, so the lab equipment actually something like this. There is a frame, metal frame, okay, in which a solid frame, in which we mount a uh, permanent magnet, north south here, and there is a coil. Okay, and this is a pivot here, and this can oscillate. So which means the permanent magnet can go through this coil back and forth. Okay, so each time it crosses the coil, I can measure the EMF. The flux changes, right? So I can measure the EMF across the coil. The coil is there, meaning a winding of copper wire, okay, which is like an inductor. So if a magnet goes through, there must be. So now the question is, okay, which I ask before introducing this experiment in the lab also, yeah, take your notebook and sketch what will be the EMF measured. In fact, in your experiment, there will be a computer which is connected to data logger, which will measure and put it on the screen. Okay, the plot of the EMF as a function of time. Okay, so now you can bring your notebook now and take your pen and then sketch what I would see if it goes through once. If this magnet goes through this coil once, what is the kind of EMF as a function of time that you would see? Please do that. Okay, and check out that you can actually plot EMF at the ends of the coil as a function of time. If you have done that, let's compare your answer. Okay, Um so I'm just saying a magnet not sought attached to an oscillating system passes through coil C periodically. So we are generating it periodically so that the computer can keep on taking pulses. Okay, but I have asked you to plot only one pulse. Okay, so now compare my answer with yours, or what is actually seen in the experiment. Okay, and, so sketch in your notebook the EMF that will appear across the coil C as a function of time t for one pass of the magnet. I hope by now you have done it. I was deliberately giving you time so that you could think it over and actually do it. So now this is your answer similar to mine. There is zero flux, initially flux change, either it is far away, okay, and then so there is zero EMF, and then as the flux as the magnet approaches, there is flux cutting increases, okay, and then when it is fully in the middle, okay, after that it tries to recede from here, and then the flux decreases. So minus d phi, the sign changes, okay, and then EMF becomes negative, and then of course if it goes other way around completely, okay, to the other side, then of course there is no flux change and again is zero. So the EMF measured across the coil looks like that, which you will measure in the. In fact, we had the setup that you will do has been designed by us in a and automated by us. Okay, it's a very famous experiment, but to suit our purposes, we have done such that you can complete it within an hour or hour and a half. The whole experiment. It is an automated experiment along with a PC. All right. So now the next question is, suppose is E as a function of time in this system. So what will be the flux as a function of time? So E, we know E is minus d phi by dt, and hence the flux phi would be simply integral of, okay. So in the lab, you would be asked to actually integrate it numerically by that is taking from what is the area under the curve from here to here, then from here, and so on and so forth. So that you can plot the the flux as a function of. So sketch in your notebook now the total flux as a function of time t for one pass of the magnet. And that would be, so each of the points actually will be measuring on screen and then plotting it. So as a function of time for the same time, the flux is this. Then of course there are many other parts of the um, experiment which you'll do. Okay, but this is in fact, you must have faced uh, uh, JE problems while preparing for JE based on this, because we have asked this many times. Okay, so you'll be doing this experiment in Physics 101 lab in an automated system designed by us. Okay, that's so we have a couple of demonstrations also in the UG lab. So once you are in the campus, you should contact the UG lab and actually do those experiments yourself. Okay, not somebody showing you. You should ask somebody to and play play around with the demonstrations. Faraday's law is something which is widely used. Our civilization in some okay, is based on lots of things. Of course, motional EMF through motors and generators, but let's say an application in which a metal detector. Okay, so you are entering a railway platform or an airport, and a security person uh, holds something in his hand and then tries to see if you're carrying a gun. Okay, that's based on Faraday's law. You can try and think out how. Okay. So this is an experiment, which is a famous experiment which you have in the lab, and please. So there is a solenoid, and there is a copper ring kept on top of it. As soon as there is a switch, actually, if you switch on the current, then the ring flies off. Okay. So the jumping ring demonstration. So if you wind a solenoid coil around an iron core, the iron core is there to to beef up the magnetic field. You know, now you know how magnetic field magnetizes the iron, and that's how it increases the magnetic field inside. And place a metal ring on top and plug the thing in, they will jump several feet in the air. Why? Okay, so you have to reason it out. I'm sure you have done that earlier. So similarly, there is another demonstration here. Actually, you could make measurement. Okay, that there is a I describe it. Okay, a short is a cylindrical bar magnet. Okay, is dropped down a vertical aluminum pipe, quite large. Okay, slightly of larger diameter, about 2 meters long. Okay, in our experiment also, it takes several seconds for the falling magnet to emerge at the end. Okay, whereas exactly similar piece of unmagnetized iron makes the strip in a fraction of a second. So then, if you unmagnetized, just iron, and a magnetized iron, which is, let's say, a magnet, okay, they take a very different time to fall. Okay, explain why the magnet falls more slowly. I'm sure you have come across this, but argue it out. So these two, we have a couple of other demonstrators, and once you are in the campus, please make sure you see them or do them. All right. So let's take the one of the nicest demonstration of this Faraday's insight that a changing B field must be giving rise to a electric field, even without any charge, unbalanced charge around. Okay, so I think this experiment is one of the nicest demonstration of that. Okay, there is no other explanation one could do. That is, yeah, let's take a line charge lambda glued onto the rim of a wheel of radius b, which is then suspended horizontally. Okay, so that it's horizontal, so that it is free to rotate. In the central region, out to radius, let's say a, b is larger. There is a uniform magnetic field B naught pointing up, right? And now we someone turns off the field off. There was a field, and we can switch off the field by the field is created, let's say, by a solenoid, and you switch off the current to the solenoid, the field goes to zero. Okay, what happens to the suspended magnet, a suspended wheel? Okay, so that is the experimental arrangement. So this suspended to an wire, let's say, and horizontal, and the magnetic field is only till A. Okay, so the rim of the well is out, much larger. So this does not cross the magnetic field at all. Okay, so if you switch off the field, and then what you would see is that actually the rim, if it is free to rotate, it will rotate, okay, in this direction. All right. So turning the field off leads to induced electric field curling around the axis, okay, everywhere. And so it must be curling around this rim also. So, and the Lenge's law dictates the direction, such that it is the field is changing and the current would flow such that it beeps up the flux, because Lenge's law says that, or we know because of the minus sign in Faraday's law, it will try to oppose the reduction of the flux in that direction. So the current, the new current that will flow in the rim, in the metal rim, would be in such a way that magnetic field is increased in that direction because it is changing from outside, and hence the direction of the current is in this direction. All right. And so we could say that there is, so why, how could this happen? This could happen only if there is, because there is a current, meanings there is charges moving. If charges are moving, there is no magnetic field here, and hence that by changing magnetic field there must have been a electric field going around, and because of the symmetry I can say that E is same everywhere. Okay, we have set it up in such a way, and so I can take E out, and this radius is 2 pi b, and that must be equal to minus d phi by dt. When I switched off the magnetic field, flux was changing. Okay, and so that is minus pi s square by dB by dt. Okay, so pi s square b is the flux, and so minus pi s square is the area, and dB by dt. So, and then hence I can calculate E. Okay, so E is of course in phi direction. Direction I know from the, and pi s square. Okay, dB by dt. Okay, so over this, so this 2ab. Okay, so E2ab is minus pi s square dB by dt, and that gives me the electric field. The direction is, of course, in the phi direction, circumferential. The magnetic field change was happening axially, and hence the electric field induced will be circumferential. It is a cross product. Del cross E is minus dB by dt. Okay, so that is my E. So now this E, what will do? This, what will the torque on a any particular segment DL, let's say? So DL, so there is that the torque would be R cross F. There is a force. Okay, or we could say it's lambda is the charge here, so there is B lambda EDL. Okay, so this is a static charge. Okay, that is to this rim. Okay, so you can think as a insulator rim. Okay, but I have stuck a static charge here. So, okay, so there will be lambda EDL is a torque. So the torque is B lambda minus a square by 2b dB by dt. Okay, because it's a constant I can take out. Okay, and then there is integral of del, and hence that is nothing but, so minus b lambda pi a square dB by dt. All right. So angular momentum of the wheel then, okay, this is the torque. Okay, so angular momentum of the wheel would be, of course, n integrated over time. Okay, and so that is, initially we started off with b naught and to 0, so dB by dt, so dB is going to be to 0, and that is b lambda pi a square b naught. Now the total angular momentum achieved is only depends on b naught, not at the rate at which you switched it off. So it's, so after you switched it off, then it has acquired angular momentum. Okay. So would it matter how quickly or slowly you turned off the B field? No. All right. So there is angular momentum. But the question remains, who did the rotating? no B is present at this static charge lambda. So no B is present at the wheel. So obviously, as I said, okay. Uh, so the question is, all right. You saw that I used a technique, as I had earlier indicated, that E dot dl is minus d phi by dt, whereas minus d phi by dt is playing the role of B dot dl mu naught inc. Okay, but that's just very specifically a magnetostatic technique where time was not varying. So are you justified in using a magnetostatic technique in a time varying problem? We had just noted the formal equation wise the equivalence between the two sets of equations. Okay. So as we'll see that, well, yes, you can do that, okay, which is called under quasi-static conditions. Magnetostatics is valid until and unless you are actually going into very high rate of change, which will be in a wave. Okay, much lower than that, most of the time, the magnetostatics can be used. So unless you go to speeds, okay, which is clearly close to light or something, okay, we'll see the condition the under which quasi-static approximation is valid in the next section. But under quasi-static conditions, you can actually use that. All right. So this was a nice example. You could explain it no way but by the induced electric field because of the changing magnetic field. Okay. And but the remaining question. Okay, where did this angular momentum came from? Initially, everything was so. Angular momentum conservation is not valid because there is no external force from here. Okay, so there was everything that was internal to the system. Okay, so that's something that we hope we'll be able to do it in the next few lectures. That the actually the field itself, okay, stores angular momentum, both linear and angular momentum. All right, so that's something that we learn as we go along. So induced E in a solenoid in a quasi-static approximation. So let's assume that I have a solenoid, a long solenoid with radius A and n turns per unit length, carries time-dependent current, IT, in the phi direction. Okay, and so find the electric field magnitude and direction at a distance s from the axis, both inside and outside the solenoid, okay, in the quasi-static approximation. That is, I is a function of time, but it is function in time such that magnetostatics is valid. So that is what I mean by quasi-static approximation. It's not so far, it's not like the speed of light is involved in change of I, okay, much less than that. So there is a quantitative criteria we can put it, but that will do it in the, so that is of course pretty easy. So let me try to plot uh, the solenoid. Okay, Now, a simple model of a solenoid with a radius a and n turns per length, and I'm changing this I that is going around. All right. So in the quasi-static approximation, magnetostatics is approximately, magnetostatics is valid, let's say. Okay, and so B inside, of course, then it'll be mu naught I Ni, n is n turns per unit length, Ni in the k direction. This is circumferential in phi direction, and S less than A. In order to B out, if it's a long solenoid, then of course B out is 0. We know that. This is directly taken from magnetostatics. Okay, saying that since it is quasi-static, I can directly use my magnetostatic results. All right. So then I take an Amperian loop inside. Okay. Now I'm using Amperian loop in the new sense. Okay. So choosing an Amperian loop which is less than S less than A, I can say that what is the phi is B pi I square. B is mu Ni, okay, and the loop is also pointing in this direction. So mu Ni pi S square. Yes. So then, of course, E dot dl is what is E is same everywhere, okay, because of the symmetry. So E2 pi line integral of E dot dl, E2 pi S is minus d phi by dt. Phi I already know, minus mu n pi s square di by dt. So if I know I is a function of t, then di dt. For example, if it is sinusoidal, sine omega t, then this will be I naught cos omega t. Okay, or if it is cos omega t, this will be plus sine omega t. So this is di by dt. So then E is mu naught ns di by dt, and E is in the phi direction. All right. So we have used the sort of Amperian loop, the magnetostatic results, and that's is allowed by this quasi-static approximation. Okay. So choosing an Amperian loop which is outside. Okay. So now there is no magnetic field outside, but I have taken, but there is field crossing, just like the last example. All right. So the phi is of course now b s square. A is the width of the sorry, the radius of the coil. So mu naught ni. So the total phi is only inside the solenoid. So mu ni pi a square, but there is still an electric field getting induced in the in this circle. So E dot dl is now E2 pi s. S is greater than A, and minus d phi by dt. So this is again minus mu naught n pi s squared di by dt. Instead of s, it is a square, because this the magnetic field is only confined to radius a. All right. So that will give me now divided by 2 pi s a square di by dt phi. Okay. So now you can see electric field magnitude is falling off as 1 by s outside. Okay. Everywhere it is still in phi direction, but the strength of the induced electric field is falling off as 1 by s. Strength of the induced electric field inside the coil is linearly changing with s. The direction is phi in both cases. Okay, but here it builds up as s goes up, and then here it drops off outside as 1 by s. Okay, so these conclusions were all possible under quasi-static approximation and using the technique of Amperian loop used for the minus d phi by dt as if it is mu naught inc, I enclosed. All right. So I'll stop here, and then we'll take up the next thing is magnetic induction, the mutual inductance and magnetic energy.